Hey there everybody, this is a video for my grade 12 pre-calculus students. In this video we're going to look at the natural log and the base e. If you were doing what you were supposed to be doing and following my blog, you were supposed to have watched a number file video before this video. If you decided to skip the number file video and go straight to this one, you might want to backtrack. That number file video is really good and it helps to introduce the concept of e. I'm going to just go in a little different direction for a minute and just talk about what are logs for anyway. We've done some word problems, we've done some applications, but John Napier invented logs back in the 16th century, the early 16th century, because he was looking for a way to solve problems that were really hard to do in his time, one of which was just working with really big numbers. Remember when I write the word log and I write it symbolically like this, that means I assume without a base given here that it's a base of 10. So the log of a billion is simply 9 because 10 to the power of 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So think about the simplification that happens with great big numbers by turning them into logs. Logarithms helped mathematicians in those days work with really large numbers in a way that was very, very efficient. John Napier was an interesting guy. Just looking at his Wikipedia page here, we credit him with being kind of the first mathematician to commonly use a decimal as a dot in math. Before that, it was commas or just using gaps. And I love the way they say he discovered logarithms. I don't know if it's a discovery or an invention, but he certainly did popularize logarithms. And the main use for logarithms in those days, check out his page if you want to read more about him. He was an interesting dude. The main use in those days was to, again, simplify very large numbers. The other major application, of course, is to solve equations where the variable is an exponent. How do you solve that without logarithms? Well, you could guess and check if you liked. You know that 2 to the power of 3 is 8. And you know that 2 to the power of 4 is 16. So you know that this x here has to be 3 point something. But that's about it. You're just estimating. Whereas if you were to take this equation and take the log of both sides, it becomes quite easy to do given a logarithm background. This exponent becomes a coefficient. And then I just divide both sides of the equation by the log to the base 10 of 2. And I actually don't even need a calculator for the top part. Again, log to the base 10 of 10 is like saying how many times do you have to times 10 to get to 10? And the answer is, well, you only need 1 10 to make it to 10. So the numerator is 1. And of course, in Napier's day, he wouldn't have known exactly what the log of 2 is. He would have had that worked out on a table system, and you'd have just looked up the number from a table. Of course, we don't have to do that. We can just punch buttons on even a fairly simple scientific calculator, and we know that the log of 2 is, where's the log on this thing? There we go, is about 0.301. So this is like saying 1 divided by 0.301 roughly. And even in the days before, remember, Napier's work in the early 16th century is about 200 years before Charles Babbage came along and invented the adding machine. So they didn't, not only did they not have calculators, they didn't even have adding machines. So really large numbers were tough to work with. And questions like this would have been pretty much impossible to get very accurate answers from without logarithms. So from a logarithm table, you look up that number and then just do the divide. So I can just reciprocal that number, and there you go. The right answer here is 3.32, and I can prove that that's true by just storing that number and say, I don't know, memory 1, and then go, okay, so 2 to the power of my memory 1, and that should give me 10. So that's what logarithms are for. Now, of course, nowadays we certainly aren't scared of big numbers. We have scientific notation, we have very powerful computers and calculators that can work with big numbers for us. And even stuff like this seems kind of like a trivial use of logarithms What keeps them around, besides the fact that they can be used to solve for unknown variables, is the fact that in problems involving growth, logarithms pop up a whole bunch. Now, the two common log bases that people use the most are, of course, the log, which is just to the base 10. So again, the log of 10 is going to be 1, the log of 100 is going to be 2, etc., because I assume this to be base 10. But that's not the only base we could use. We could even use a base of 2. Counting systems with bases of 2 are actually pretty common. That's how computers count, right? They only use 1s and 0s. They use binary code. So log to the base 2 of, say, 2 would, of course, be 1. Log to the base 2 of 4 would be 2, because 2 squared is 4, etc. But the most common base that pops up in the sciences, and not just the hard sciences like physics and chemistry, but also the social sciences, where you talk about population growth, even in the business world, when you talk about interest rates and growth of wealth, the most common base, oddly enough, is this weird number e. So going to our notes, e, as you found out in the other video, is 2.718281828. Now, that looks like it's going to be a repeating number. It isn't. Don't let this fool you. This is not a repeating number here. Here it is on a very powerful calculator. Use the computer ones. You can see that e doesn't come close to being repeating. It is irrational, just like pi. It is what we call a transcendental number, like pi, which means that there's no way to come up with a polynomial equation that solves to have e as a root. And in the video you watch, they talk about that. Pi you can at least find using geometry. E you can only find by studying something that grows naturally. It's called the natural log number. So we have a different way of writing logarithm if e is our base. If we want 10 to be our base, we just have to write log. If we want 2 to be our base, we write log 2. If we want pi to be our base, we could write log to the base of pi. Could you imagine how many times you times pi together to get to a number? But you could do it. There's nothing wrong with that. But if you're going to use e as your base, instead of writing log, you write, instead of writing it log, you write it ln. Oh, I froze. Come back. There we go. You write ln, which means the natural log. Some people call it ln. Some math teachers get really mad when you call it ln, like it's this dumb nickname. Those are the same guys who don't like square roots of negatives to be called imaginary numbers. But the nickname's kind of stuck. So you'll hear me say ln instead of log. But ln is the natural logarithm, and as soon as you see the symbol, you know that the base is e, so you don't have to actually talk about it. If you want to find e on your calculator, it's not that hard to do. If you have this kind of calculator, the kind you actually look for the natural log button, and this is the kind of calculator where if you want to do something like square root 16, you have to hit the square root first, right? And then square root 16 is 4. If you want to do sine of 30 degrees, you'd go sine 30, and you hit it in the same order. You kind of write it down. So logarithms the same way. If you want the logarithm of a number, you just type the log of, again, 10, and I know that's going to be 1. Well, if I want e, notice that it's the shift. I don't know if you can see that or not, but it's always the shift of the natural log button. So if you actually want the e number, you have to go second function and then that, and it'll say e to what power would you like? And of course, if I want e itself, I'll just hit power of 1. And there you go, there's that e number. And again, on a smaller screen there, it does look like it's repeating, but again, as we saw in the other calculator, it is not. Some calculators are fancier, like the computer calculator, where you can just have an e button. You don't have to trick it into telling you an exponent and make the exponent 1. On a calculator that works in the opposite order, for this kind of calculator, if you want, say, the square root of 16, you have to put 16 on the screen and then square root it. If you want the sine of 30 degrees, you need the 30 on the screen and then sine. So if I want e, I hit 1, and then I take the inverse natural log of that, and boom, there's your e number. Now, if you're wondering why do they make e so hard to find on a calculator, it's because you don't actually punch in e very often. You don't use the number directly so much as you use the natural log. In other words, this is saying I would like to calculate how many e's I got to multiply together to get to 5/3. So I would punch that into my calculator as the natural log of, and I might as well just open a bracket, 5 divided by 3, and boom, there's the answer. It's about, I don't know, 0.5108. I'll just round it to 3 places. What's after the 8 of 2? Okay, so it's 0.510, 4 places, I guess, 8, and then blah, blah, blah. Okay, so that's how you do something like that. If you had this kind of calculator, I would have to maybe get the 5/3 on the screen first, and then inverse natural. Oh, wait, not inverse. What am I doing? Sorry. 5 divided by 3, and then natural log of that, and there's the same answer, 0.5108. Okay, so there's the first one. So obviously these are all going to be using either calculators or logic. And here's what I mean by logic. Now, think about what this is saying. Remember a few minutes ago, I pointed out that log 10 is, what would log 10 be? 1. Why? Because remember, this base is 10, and 10 to the power of 1 is 10, right? That's the 10, that's the base, there's the exponent, and there's the argument, right? So basically, log to the base of x is always 1, assuming x isn't 0 or a negative. Remember, the argument of a log can't be a negative. So this is always true. So that means that this is actually, you can think of this as, first of all, remember that in logarithms, an exponent can be written as a coefficient. And then this part here is 1. So this is basically like saying 3 times 1, which is 3. So no calculator required for that one. Let's try the next one. Actually, this one here, this one took so little space that I think I'm going to use this space for C. I'm going to do it 2 different ways. I'll do it one way and then another. Okay, so first of all, I can again rewrite this. I can rewrite this whole thing by taking the log of both sides of the equation. Right? I can change this to, I'm going to take this as the log of 10 to the power of the log of 5 is equal to the log of x. Okay, and then exponents can become coefficients. So log to the base 5 times log to the base 10 is equal to log to the base x. And then, of course, log to the base 10 again is 1. Or log to the base 10 of 10, I should say, is 1. So basically this is the log of x is equal to the log of 5. So x must be 5. If you don't like that way, you notice here I could just rewrite this in log form. I could change it from an exponential equation to a log equation. So the base is 10, so I can write that as log to the base 10. And again, I didn't even need to write the 10. I could have just wrote log. So log to the base 10 of x is my argument, which is, or sorry, my argument is x, and my exponent is log 5. And once again, log to the base 10 of x equals log to the base 10 of 5, so x must be 5. Basically, you can anti-log both sides of that equation. That works for regular logarithms, and it also works for natural logarithms. So again, let me do this kind of both ways. First, I'll do it kind of the more complicated way. I'll take the natural log of both sides of the equation. So it's ln e to the ln 7 is equal to ln x. I don't want to run into that one. So then this becomes the coefficient. And then this is 1. So ln of 7 equals ln of x, so x must equal 7. Let me do it the easier way. Let's change this again into a natural log equation. So that means that the base is e, so it's natural log, and again, I don't have to write e, I know that's the base. And the answer is my exponent, so that's my argument. And this exponent, of course, again becomes my answer. And then x is equal to 7. Okay, so natural logs work the same way as the standard logarithms. Okay, so we can do more complicated things now. For example, I'm going to do this one by, again, finding the natural log of both sides of the equation. So I'm going to take the natural log of e to the 2t minus 1, and that's equal to the natural log of 5. Exponents become coefficients in logarithm equations. And then, from there, I can, let's see, well, I have the ln of e is, of course, 1, right? Or, yeah, the ln of e is 1. So that's 2t minus 1 is equal to the ln of 5. Okay, and then from there, I'm going to say that 2t is equal to the ln of 5 plus 1. And t then is going to equal the ln of 5 plus 1 over 2. And if I was working without a calculator, I'd be done there. If I had a table, I could look up the natural log of 5. But if I'm going to punch buttons, I'm going to punch buttons. So let's see, this is with a calculator. So I'm going to open a bracket because I have to show the calculator that I'm doing that add before that divide. So I'm going to go, let's see, where are you, natural log on this calculator? There you go, natural log of 5 plus 1. Close the bracket, divide by 2 is equal to, and there we go, 1.3, I'll round it to 4 places again, 3047. And just for fun, if you wanted to make sure that you actually had the right answer, you could, now I don't know if this is going to work. I'll try it. Okay, remember that this calculator has an answer button, so it should remember that number. And I can again find E by going, let's see, where are you, E? I can go the natural log inverse of 1. So e to the power of 1, there you are, there's E. So the equation is e to the power of, oh, that's not going to work though, because now that's not my last answer. I can't use the answer button. Okay, fancy that. I'm going to change my tactic. I'm going to use my store. So I'm going to go back to the old last calculation. Sorry, I should have thought of that ahead of time. The ln of 5 plus 1, close brackets, divide by 2. Okay, there it is. There's that number, 1.3 and change. So I'm going to store that in memory A. Okay, so there we go. So now I'm going to go get E. So there's E. Okay, so this number E to the power of 2 times the thing in my memory minus 1. So E, actually now that I think about it, I guess I didn't really need to actually get E. I could have just gone there. Oops, I could have just gone there. E to the power of, and then okay, so I'm going to open a bracket, and I'm going to go and ask it for my answer from memory 1. Oh, it wasn't memory 1. No, it was memory A. Oh, this is why you don't use a calculator you're not very used to. There we go. To the power of recall A. There we go. Times 2 minus 1, close brackets, and equals, ta-da, 5. So yep, that is the correct value for t. Okay, let's see if I can do this one without goofing it up so much. Once again, I'm going to take the natural log of both sides. And once again, when I'm in logarithms, exponents become coefficients. Okay, now, the ln of e is just 1. So this is x equals x plus 1 times the ln of 2. How do I deal with that? Well, I'm going to have to collect the like terms. I'm going to have to collect those x's to solve for x. So that means I'm going to have to expand that bracket. I'm going to have to use the distributive property. So this is ln 2x plus ln 2, right? Because remember, ln 2 is just some oogly little decimal. So that's just a coefficient on that x. Move that over, and I have x minus ln 2x is equal to ln 2. Factor out my x, and I could have used more room to finish this, and then divide both sides of this equation by 1 minus ln 2, and x is going to equal the ln of 2 divided by 1 minus the ln of 2. So now we punch buttons like trained monkey. Ln of 2 divide by, open a bracket, 1 minus the natural log of 2. Close brackets equals, and the answer is 2. That's a point, right? Yeah, 2.25 and change. So 2.25, I'll round it to 4 places again. 1, 2, 3, 4, so it'd be 89. And again, if I wanted to make sure that that was the right answer, I could store it and then run it through and see if e to that power is equal to 2 to that power plus 1. It should. Pretty sure we got that right. Okay, so want to see what that looks like on this calculator? For those of you still rocking one of these kinds. So again, if I want to punch that on the calculator, I have to put the 2 on the screen. I said a 2, not a 5. I have to put the 2 on the screen first, find the natural log of that, divide by, open a bracket so that it knows to do this subtract before the divide, 1 minus 2 natural log, close the brackets, don't forget to hit equals. Remember, that's not the answer yet, that's just what was in that denominator of bracket. Boom, there's the same number. Okay? Feel free to rewind that part of the video if you're having trouble punching buttons when you're doing these kinds of questions. And let's move on to a couple tougher ones. All right. E to the natural log of 2y minus 1 equals 5. Okay, so I'm again going to take the natural log of both sides of the equation. And why don't I just skip a step? I already know this is going to be 2y minus 1 out here because that's going to become a coefficient. And that's going to then equal the natural log of 5. Okay, so the ln of e is quite simply just 1. So 2y minus 1 is equal to the ln of 5. So from there, I can just say, all right, so hang on. Oh, hang on. I missed a ln. There's a ln here. Sorry, I didn't see that tiny little ln. Sorry, my eyes aren't so good. There we go. So there we go. Ln of 2y minus 1 is equal to the ln of 5. Now I have the natural log of something on this side. I have the natural log of something on that side. I can anti-log both sides of the equation. And then I get 2y minus 1 is equal to 5. So 2y is equal to 6. So y is equal to 3. And again, you could do a check if you wanted to. You could say that, all right, so e to the power of, open a bracket, the natural log of 2 times 3 minus 1, which is 6 minus 1, which is 5, should equal 5. And it does. And it should make sense that it is equal to 5 when you look at the structure of that equation. Okay, this guy. This one's a little more algebraic. All right, so this one's already kind of in ln form. It's already a logarithm. So I'm not going to take the log of both sides, and I can't anti-log both sides because notice there's this constant here, which means it isn't a logarithm on both sides of the equation only. So I can't just anti-log both sides. So you know what I'm going to do? This is what I'm going to do. I know what 1 is. I can re-express 1. 1 is equal to the natural log of e. So I am going to rewrite this as ln of x plus 1 is equal to the ln of e plus the ln of x. And then I'm going to use my log laws. Remember that logs added together are actually something I can represent as a multiply. Now I can anti-log both sides of the equation because those are full logarithms. So x plus 1 is equal to e times x. Collect your like terms. 1 is equal to e times x minus x. Factor out x, and 1 is equal to x times 1, or I should say e minus 1. That's an e minus 1, right? The e's first. And then divide both sides of the equation by e minus 1. So x is equal to 1 over e minus 1. And I am going to actually have to calculate that one using my calculator. So I'm going to have to actually get e here. So that's going to be 1 divided by, open a bracket. And again, the easiest way to get e in a calculator is to inverse log and then punch in a 1. And then minus 1, close brackets, equals, and the answer is 0.5189. If I rounded it, it'd be 0.5820. And again, you can check, but I know that's the right answer. And again, I wanted to see how I'd punch that on this calculator. A little tougher. 1 divided by And then to get, I still open a bracket. Then remember, to get e, I have to put 1 on the screen and then inverse natural log it. And then minus 1, close the bracket. Don't forget to hit equals. There it is, 0.582. Okay, now a word problem. Now a word from our problem solving. The value of e is often used to solve exponential application problems. It's because, as you saw in the other video, let me just jump over to Desmos here. You've seen me graph logarithms before, right? If I ask you to just graph me, 2 to the power of x, or anything to the power of x, it always goes through here because remember, anything to the power of 0 except for 0 itself is always going to be 1. But if you change this number, of course, to 3 or 4 or 7 or whatever, it doesn't change the curve very much, and it always goes through 0, 1, because again, any base except for 0 to the power of 0 is always 1. What if instead of a base like a whole number, what if we used e? Well, what happens is, you notice that doesn't look a whole lot different than just, well, y equals 2 to the power of x, and it's maybe not that much different than y equals 3, y equals 3 to the power of x. It's kind of between them, which makes sense because, as we just found out, e is 2.718 blah blah blah. It's between 2 and 3. But this graph is special, as you learned in the other video, because every point along here, if you found its coordinate, it would actually always be the value of the natural log of x is the y. You would also find that if you found the area under every dot on that curve, it would always equal the y value of this coordinate. So if you calculated the area, let's use a nice easy one here, about 2. Oh, come on, 2. Okay, never mind. I can't make it exactly land on 2, but you get the idea. If I were to find the area, if I were to draw a line straight down from that dot and then color in all of the area under the curve, it would add up to 1.974. No other base will behave that way. And of course, if I'm figuring out something, say that this is a population that's growing, like, for example, the population of COVID patients, then this curve, of course, gets smaller if I put like decimal numbers here, right? That this is what we're doing. We're trying to do the flattening of the curve, as they say. We know that all population growth is going to happen exponentially, but if the number here, that if x represents the number of patients with COVID, and this this variable here represents the rate at which they're getting infected, if we cut that rate down, we, as they say in the media, flatten that curve. So if the transmission rate of a disease goes down, the curve gets flatter. So what does that have to do with population growth? Well, let's take a look at, again, an example here. Let's go to a mice problem. There are 500 mice found in a field on June the 1st. On June the 20th, 800 mice are counted. If the population of mice continues to increase at the same rate, determine how many mice there'll be on June the 28th. Use the formula A is equal to P times e to the RT, where P is the initial value, A is the final value, T is the time in days, and of course we were already told that that's going to be 20 days, and R is the rate of increase or decrease. So notice that if R is greater than 0, then the function increases exponentially. If R was negative, then the function decreases exponentially. That would be like a decay problem. So we actually don't know what R is, but they tell us that on June the 20th, there's 800 mice. So the amount of mice I have is 800. The final value is 800. The initial value is 500. So that's the P value. And we know E is the value 2.9 or 2.718 blah blah blah, but we don't know this R, and we actually know that the time is 20 days. So I'm solving for this R. So how am I going to do it? Well, first of all, how about I divide both sides of the equation by 500? So that's actually 8/5. I'm going to cancel the zeros out, and let's rearrange that. Let's go 20R. Make that a little more easy to read. Then I'm going to take the natural log of both sides of the equation. Okay? And, oh yeah, exponents become coefficients, and the log, the natural log of e, is just 1. Remember? So this thing here is 1. So that's it. That's the equation. So I can say that r is the ln of 8/5 divided by 20. Button punch time. I'll use this calculator. So 8/5, which is 1.6. Like I needed that. I could have figured out that was 1.6. But anyway, natural log divided by 20. And there we go. That's 0.0235. And that's a decimal. Usually in problems like this, you might want to change that to a percent. So 2 point, right, when you times by 100, you'd move it to there. 2.35, what's after the 5? Yep, 2.35%. So therefore, there we go. That is the growth rate of the mice. Okay, so now that I know R, and I'm not going to erase that number. In fact, why don't I store it? I will store it in memory 1. There we go. Now, let's use the formula again because we want to find out how many mice there'll be on June the 28th. So A is equal to, so now that 500 is my starting point, E, and now I know R is 0.0235. Remember, you got to go back to a decimal. You can't put percents in your formula. And I know that T is 28, so that's 500 times, and again, to find E, I just have to go inverse that. Oh, right. Oh, I got to put it on the screen first. 500 times, and then I have to go 1 inverse, where are you? Natural log. There we go. That number to the power of, and then I'm going to open a bracket, recall that number, times 28, close brackets, and hit equals. And there we go. The answer is 965, I'll round it, mice. Okay, on this kind of calculator, it's actually much easier to punch what I just did. It'd be 500 times, and then this button here gets E all ready for that big ugly exponent. Oh, but I don't actually have the other number. I guess I should go back and get that. I'll do that first. So let's see, that was the, what was it again? It was the natural log of 8/5 divided by 20. There we go. And now this calculator too, the another advantage this one has over the other one is it has that answer button. So it'll remember that number in my next calculation. So 500 times, and then E to the power of, open a bracket, and then my answer times 28, close brackets, equals 965 mice. Okay, so your homework will have a few questions kind of like this. We're not going to do all of the homework questions. The next page in the book is a big page of word problems, but I haven't done examples on things like compound interest and stuff. I figure you'll be taking business courses if you're going into the Asper School of Business or whatever. They'll teach you how to do that. So that was something I decided to cut for time from this unit. So we'll stick to the questions that involve stuff similar to the examples we did. And then there is one more assignment in the assignment book. And again, I'll just pick and choose which questions I want you to do. Go check that out on the blog. Thanks for watching, and that's the last lesson from Chapter 8.